So you finally do a projection, pi s name here, right? So I think this will make sense to everybody, right? Yeah. Okay. So this is solution one, but is this the only way to write this? Can anybody suggest a better way to write this?
Rather than do natural join, couldn't you do an equity join?
Natural join is actually equality join. Natural join is equality join, just on the same two columns with the same name. So that's the definition of natural.
Okay.
Do the selection first, so you get a smaller subset before you do the join. That way you're not joining as many records.
Yes, correct. That is a better way to do it. Basically, you can push down the selection operator across the join. Basically, you first do the selection, then you do the join. This way, you will end up with a much smaller base table because you do the filter first. Because you have fewer records on the left-hand side of join, that will result in a much faster join operation, and finally you do this projection. That's the same. So yeah, this is a better way. So basically, in relational algebra, in a real database system, what database system try to express a SQL statement is it uses the relational algebra. So suppose first it will end up with the solution 2, but it will have some component called optimizer, as I talked before. This optimizer will try to find an equivalent relational algebra that is more efficient, just in this case, just like in this case. Suppose you first come up with solution 2, then the optimizer realizes, hey, I can push that select operator across the join, so that I can get a much smaller base table for the joins, and that's faster. So you will decide I will stick to the solution 1 instead of 2. That's the role of your database system. Yeah.
Do we have to say where the sailor SID to the other SID when we do the join?
You mean other attributes?
Yeah, like we're going to say the sailor SID to the SID.
Yes. So basically, if you do not specify anything in the natural join, it's just joining those columns with the same name. So in this case, just the SID. All other things just get appended to the column. Does that make sense?
So you don't need to do sailor SID, you use SID.
Right. You can just don't write it. It's okay because here they have the same name, right? Yeah. Does that make sense?
So you're assuming it's already done.
Yeah, it's just its default meaning if you don't specify anything. Yeah. All right. So let's see the next example. So find the names of the sailors who reserved the red boat, right? So does anybody know how to solve this?
What's the schema for the boat?
Let me see. Yeah, this is the schema. You have boat ID, boat name, and color. Just change this a little bit. This is the name. The name. So this is the color, right? And some name. Okay. So how do you solve this?
You join the boat with the reservation column.
Yeah.
And then you can either join that with the sailor column as well, or you can select or project out the SID from that and join it with the or sorry, first you need to select out the boats that are red and then you project out the...
That's correct. So basically you're saying is you can select out all the red boats in the boat table, then join reserves, then join the sailors. That way you can find all the reservation record from some sailor who's reserved the red boat and project that out to only the sailor names. Right? This way you get the final answer. Yeah. But there's also optimization opportunity because as you said, you can project things out before you complete the joins because you only need some of the columns there. So what you can do is once you select the red bolts from the bolt table, you can just project to the bolt IDs because you only need the bolt ID. The bolt names are not relevant, right? And the second thing to do, once you join that with the reserve table, you only need the SIDs of those sailors who's ever reserved the red bolts, right? So you can also project that to only the SIDs. Then use those only use those SIDs to join the sailors table to find out the names of those sailors. Does that make sense? So this is actually an example. So of what another example what Query Optimizer can do. So basically, if you come up with the first algebra, relational algebra, you want to do this more efficiently. So a Query Optimizer should be figure the second algebra out based on the first one, because they have the same semantics, but the second one passes less data through the whole system, so that it can run faster. Does that make sense? Alright. So the third example is called find sailors who reserve a red or a green boat. So how do you do that? Sorry. Can you come and write it?
Color equal to red.
Oh, you mean you can write color somewhere? You do a select color. I'm sorry. Sigma color equal to red or green.
Green.
Sorry, green. How do you write it?
Green.
What color equals green?
Yeah. So do you write something here? So just write green here. Sorry. Yeah. Yeah. So actually, this won't work, right? Because if you write a or operator, if that's what you're thinking, this won't work, right? I'm sorry, this will work. I'm sorry, I'm wrong. At least I was confused. Yeah, this one will work, right? Because if you write this on the boat table, it will filter out all the boats with the green color or the red color, right? So this will work. So this is exactly the solution. So you can filter out the red boats or the green boats, then do the same as the previous ones. I'm sorry about that. Yeah, misunderstood. Yep.
So we need one equal sign.
Sorry?
We need one equal sign.
Only need one equal sign?
Never mind.
Yeah. Okay. Yeah. Yeah, but for this one, this is different. So if you want to find a sailor who reserved the red and the green boat in history. So how do you do that? Can you just change this to N? Can you? Yeah.
So you can't just change it to and because a boat's not green and red?
Right, that's
so
correct.
You'd have to do two queries and find all the boats that are green and all the boats that are red.
Yeah, exactly. So because this is applied to each of the elements in B, and one particular element can only have one color, right? So if you specify N here, basically you end up with nothing, right? So you cannot just change that or operator to an N. Sorry, that's what I was confused about, because this actually is different from the previous answers. So what you can do is you can use a union operator. What do? You first find all the sailors who've ever reserved the green boat. Then you find out all the sailors who've ever reserved the red boat. Then you do a union. Yeah.
I mean, union will give us all the answers
Right.
from both the sets, but we need intersection.
Oh, sorry. Yeah. I was wrong. You've seen the section. I'm so sorry.
But you can use the division operator as well, right?
Division will work. If you have some answer, can you tell me now?
Like,
No, we need union.
red and green case. So this green is like
So greens and
one
reds are
into
separate,
the
right?
case
And
that
you
we
need both of them.
Oh, I see. Yeah. So
Union
yeah,
reserves.
that is
People
actually
have
a clever
reserved
solution.
a
So
red.
you can
So
do
for us,
basically
like
select
5 people have reserved red, 3 people
color
have reserved
equal
green.
to
So we
red.
get 8 if we do union.
or
I mean,
color
5.
equal to green, right? Then before you do the division, you need to do a pi, right? Project that to only
So
the
before-
color,
yeah.
right?
Before doing an intersection, you need to project out only the name. No.
Sorry?
Because intersection would be 0, right?
No, this is fine because this is OR. It won't be containing only 0 rows,
We
right?
will need
You
union.
can just project this to the
That's
colors
fine.
so that this will be just green and red, right? Green and red, two values here, right? And then you do a division. So basically both pi of the BID and color of both.
Division solves it.
You use a division here to find all the boats. Sorry, you need to do boats join reservation. Yeah. Then you get all the reservation record with their boat colors. Then you do this division to. Sorry, this should be SID and color, right? Then you do this division. You find all the SIDs with all the colors shown here. That's green and red, right? Yeah. But just wait a second, because I will figure out, I will point out this might not work in one certain case. Can you give me an example? I'll show you one particular case that it doesn't work. Anybody can give an example, counter example to this?
There's no sailor reserve both.
No sailors reserve red boat. No, that's actually okay. So if something doesn't come up in reserve, that's fine. But the only thing that means that's troublesome is if something is missing from the boat. That's to say if you don't have a boat, that's red. Then you only end up with green here, say. Then this will only find out all the sailors who's ever reserved a green boat. Right. So that's why this division may or may not work. Yeah.
Another problem is that you have two different boats and they're both red.
Yeah.
Then the sailor would have needed to reserve both of the red boats.
Oh, actually that's fine because here you do a projection here, right? So because you projected that BID out, so it's not there, so you don't have to reserve both boats, right? So this actually it will work in a general case. If you are sure there's both red boat and a green boat, but if not, then this won't work, right? Yeah. So for a more general answer to a more general input, it would be you first find all the red boats, everyone who's reserved red boats and everyone who's reserved the green boat, then do an intersection of them, so that you can find those sailors. That's the most general answer, but in certain cases, of course, this division will also work. Just if you are sure there's both a red boat and a green boat. Yeah.
So why couldn't we use the top, the and symbol?
The and symbol?
Yeah.
Yeah, this is because the sigma operator is applied to each item in this boat. So that means I will give you one item, say one red here. Can you say it's both red and green? No. So for any of them, you cannot have both red and green boats, right? So that's to say this condition is never satisfied. So this will end up with an empty set. So that's why this won't work. But if this is OR, then it will work because if it's OR, one boat can be either red or green. That's fine, right? So that's the difference between this one and the previous one. All
And we
right?
can use union operator here instead of intersection, then we will get the OR thing.
Yes, that's correct. So if you use union here, you can also get the answer for the previous one, right? So that's a little bit tricky. So basically, intersection and union, they are gonna both apply to both questions, but for the second one, you can also only use a union. An intersection instead of just or, right? So is that clear?
question.
Yeah.
That I think, for example, can we do something to modify the division, the division here? Because I think that maybe there is some cases where kind of we not say that we find the sailor who reserve the red book and green book. Sometimes we can provide a table or all kind of books, and also we have to find a sailor who reserve all the votes in the table.
Okay.
Not kind of explicitly like red and green, and we have the union kind of.
Yes.
manual.
So if you are trying to find the sailors who's reserved all the the boats of all the colors you have in the inventory. Yes, then this is the solution. Basically, you just drop this selection here, right? But suppose you are specifying something specifically that you are interested in, then this will, sometimes it won't work, right? In some cases it won't work. That's the key point. But of course, in reality, of course, you can just specify a value. If this is single query, you can just specify some values like red and green in your statement. So that won't be a problem. But in relational algebra, you don't have a way to say, I just want a set with green and red. So that's why this division won't work for every case here. Okay. Is that clear? Okay, so this is the example we've already seen about division, so we'll skip that. Yeah, so for this one, for each boat, find the sailor with the smallest sailor ID who has reserved this boat. So how do you do that?
Sort.
Aggregate? No, we don't have aggregate here yet. Sort? We don't have sort here yet. Because this is set, you cannot sort a set. How do you do that? Yeah, so this is something very similar to how we express the division operator using the basic 5 operators. So the way to do it is that we first create every possible combination based on your tables.
You get a cross check and then check less than for every.
Right. That's exactly what I'm trying to say. That's correct. So what you are doing is basically you want to find the smallest sailor ID who has reserved each boat, right? So basically, what you can try to do is you can first join this boats with the sailors. This is based, this is reserved. So based on the ID, right? This is based on the BID because this can be implicit because they share the same name. So suppose we define this as a table T1. So what's the schema of this? It's, I guess we can also do a projection here so that we don't have to worry about other stuff. We are just caring about SID and BID here, right? Smallest sailor ID, and we do a reserve join boat. This is based on BID, right? So what's the schema of your result? This T table will contain just SID and BID. All the distinct pairs that exists in your result table. So suppose you have 1, 2, 2, 2, and 1, 1. Let's add another one. Suppose it's 3, 3. Alright? Okay, so suppose this is your T table. What you do is you first do a cross product. With the cross product, you get all the possible combinations. How many combinations do we have here?
16.
16, right? So basically you have SID1, BID1, SID2, BID2. So of course, here you might want to do a renaming. Otherwise, you cannot distinguish the SID here and there, right? So basically, you can try to do this T1 here, then write the same thing here. Basically, do write this again, so that you have two different names. Then we do T1 cross product T2, and we do a selection. So what's that based on? So we want to find the smallest SID for each of the boats. So let's first ignore the boat part. That's to say, you do not want something that has a if something is larger than another, then it's not in the answer, right? One SID is larger than another SID, then it's not in the answer. So that's to say, if T1.SID is greater than T2.SID, that means for this guy, his SID is larger than another guy's, so he's not in the answer. But this is not exactly correct yet, because we need to do this for each boat. So we only, like, suppose you have this one and this one here. They basically they reserved a different boat, right? They reserved two different boats. So even if this is larger than one, it doesn't mean this guy shouldn't be this guy shouldn't be in the answer, because they are basically different boats. So how do you do that? Basically, you need to find all the pairs who have matching BIDs, right? These two should match. So that's basically a join, right? But here, can you just write nothing as the subscript to the join operator as a natural one? No. The reason is that you have two columns with the same name, right? This is the same, this is also the same. So you must specify what you want. You must specify you want the BID to be equal, but SID not necessary to be equal, right? So you change this cross product to a join, and do a selection on top of that, right? Or because this is selection and join, and this can be combined together as a join, general join. Let's just say you can write a single join. Another way to write this is to write T1.BID equal to T2.BID, and you also have to satisfy this condition. So basically, T1.SID is greater than T2.SID. These two are basically equivalent, because, as I said, this join is basically a selection plus cross product. So the selection can be combined together, two selection consecutive selection can be combined together with AND operator. So that's basically you can do here. You can basically combine these two, then as a combined select operator, you can combine that with the cross product operator as a join operator, and write a general Taylor condition here. That's also a way to write it. Does that make sense? Yeah, so in relation, the vanilla relation algebra don't have aggregation, don't have source, so that's why you have to do this in this awkward way. But this is actually the basis of your database system. Basically, modern database systems have extended this to more operators, useful operators like sort, like to by, like order by, right? But in the relational algebra, because we want to keep it simple and in the sense of mathematics, we just want the basic building blocks. So that's why we only have this.
We are having T1.SID is greater than T2.SID. Shouldn't it be less than, because we want the smallest one?
Yeah, I haven't finished yet. But let me finish this first. But I can explain that to you why that doesn't work. Okay. So with that, actually we have found out all the. So basically, in here, in the result, the T1 path has a larger SID than its counterpart in another table, right? So if we just project this thing to T1.SID, what does that mean? That basically means for each boat, the result in the result, this SID has a Sorry, we also need to include the boat ID because we want to do this for each boat, right? So for each boat here, this SID is larger than some else who's also reserved this boat in history, right? So this is not something we want. So how do we do the inverse? Basically, we do a subtraction or the set difference. So that's SID and boat ID. That's all the reservation record, and minus R. Of R. Then minus this. So basically, you find out all the things that you don't want and subtract that from all the records. So that gives you the final answer. All right? Yeah. So this is the final answer. So basically, on the left, you have everything in your reservation record, and on the right, the R part is everything that you don't want because they have their SID is larger than someone else who's reserved the same boat. Then you get the final answer because if you subtract this out, you subtract something you don't want from all the things. All the left is something you want, right? So if you write a smaller than to answer your question here, why that doesn't work? So suppose you also drop this part, why it doesn't work? That is because if you say for the same boat ID, this boat ID, this SID, for example, if the boat ID are all ones for 3 records, and there are 3 different sailors, that's 1, 2, 3. So 1 is the smallest one. Of course, his SID is smaller than someone else's, right? But also 2 is not the smallest, but he or she also has a SID that is smaller than 3. So in your answer, you will have 1 and 2, right? So that's why you cannot do this in a positive way. You must have to find the negative examples you don't want, then subtract them from all the examples. Then you get everything you want, right? Okay. And this is also basically the basic idea of the division operator. So it's roughly the same. So basically, you find out everything that who's never done something, then subtract that out from all the answers. So if you go back to that slide, you will, if you understand this, you will be able to understand that as well. All right. Yeah, this is basically the same. So I will just skip that. So in summary, we covered all the 5 basic relational algebra operators, which is select, sigma operator. Yeah.
Sorry, can you go back to why you had R1 and R2?
This one?
Yeah.
Oh, R1, R2 is basically for naming purpose. Because here, if you just do one table, say you just use a R, right? So when you use this in a join operator, how do you specify which boat ID you are specifying? Like if you say R1 join R1 there, if you say boat ID, which one are you referring to? That's a problem, right? Does that make sense?
No. So
No.
are you?
Yeah. Let me just explain this to you. So this example is basically, so suppose you have a join. Suppose you have a join, that's R1, join R1, right? And I want to write what? I want to write BID equal to BID and SID on the left greater than the SID on the right. But like this is ambiguous because you cannot, even if you add the table name here, you don't know which one are you specifying. Is this one or that one? That's ambiguous, right? Does that make sense?
Okay, so you're just doing it so you can compare it to other rows on the same table.
No, you cannot assume that. That's what I'm saying. Basically, here you cannot assume the left-hand side of this operator is from the first table. You cannot assume that. You have to clearly specify that. So they must have a different name for you to be able to do that, right? So that's why we have two different copies of that the same result. We need to have R1 and R2. Right? Does that make sense? Okay. So yeah, basically this is about the relational algebra. We have all the 5 basic operators and some compound operators: join, division, and intersection. That's everything. So so far so good. Any more questions about the relational algebra? Okay, so if you have more concerns about relational algebra, or you have any questions in your homework assignment, you can just come to my office hour or NTA's office hour. Also, basically, we are here all day, basically maybe until 5, from maybe 9 to 5 or 10 to 5. So if you have any questions, just send us an email, and if we are just at the lab, you can just come by to ask us some questions. That's fine. But just in case, if it's not the office hour, we might not be there. We might be somewhere else. Then if you come, you don't find us. That's like it's not convenient, right? So you might want to just send an email if you come not during the office hour. All right? Okay.
So when you use subtraction, you don't have the same columns.
Yes, they must have the same colors on both sides. They must have the same schema.
Okay. Then before didn't you only have SID and PID?
Yes, on both table I only have SID and PID, right? Because I did a
So
projection.
it should be a subset of you subtract. The right hand side should be a subset of the left hand side.
No, it's not a subset because the first operator I did a pi, right? I did a pi SID like that.
Or like the
Yeah, the next one. This one, right? So, yeah, so here the left hand side has only SID and PID, and the right hand side as well, right? Alright, so that's about the relational algebra, and we will start about the SQL part. Yeah. So how many of you have ever used SQL before? And yeah, that's a lot. So maybe we can, let's say this, how many of you are not very familiar with SQL? All right, yeah, that's fair enough. We will try to like make a balance of this, because like we will try to explain everything to you, because some people here still don't understand SQL or never used it before. So sorry, we cannot skip this for a lot of people. If you are familiar with SQL, maybe you can use this as a refreshment or something, right? So basically, the SQL stands for Structured Query Language. What does this structure stand for? Basically, the structure means this is a structured data. Structured data is something like tables, right? You have fixed schemas, and in schemas you have names, types, and some constraints. That's why it's called structure. All right? It's contrary to other things like a semi-structured structure or non-structured. That's something like if you have a JSON. In JSON, you can have missing fields, right? In a JSON, you don't have to have so suppose you have 2 JSON objects. They don't have to have matching fields in both objects, even if they are in the same database. So that's why we call it semi-structured, because you still have fields, you have types, that probably is implicit, but something can be missing from there. But for SQL, you must have everything. So even if the data is not there, you put a null there, but your table is fixed. You still have those columns and those types, they are fixed. That's everything, right? So yeah, the latest standard is SQL 2016. I think the previous slide, in the first slide, I put SQL 2011. That was because that slide was really old, and that was that was created before like 2016. So yeah, but the latest one is single 2016. But that doesn't matter. Nobody actually fully implements the standard. It's just like nobody makes a standard conforming C compiler, right? Nobody actually just implement those standards. In reality, people have various extensions, various dialects of the language, so they have some different functionalities or the same functionality with some different syntax. But at the core language is the same for all systems. So basically, if you know how to write select, how to write create table, how to write delete, how to write insert, you are almost fine with all systems. As a user, of course, not the administrator. Because as an administrator, you must know more about the system, about the internals, and how to tune the system. So that's a different story. But just for the query part, or just as a novice user for the database, it's fine if you just know the core SQL statements. So SQL, as we said, basically there are two main parts: the DDL language, data definition language, and the data manipulation language. So the data definition language, or DDL, is where you can define those tables, indexes, and modify schema, delete database, create namespace, create database, something like that. So at the core, the most important one is how do you create a table. Basically, create a table allows you to declare the schema of the table. So what's the elements of the schema? Basically, you have columns, right? For a column, you have column names, you have column, the data type of the column. You can define a lot of constraints of the columns. Suppose, for example, like the foreign key constraints or other general constraints, right? So this is the basic syntax. Basically, you write create table. Notice that we wrote create table in uppercase, right? But in reality, in most systems, it is not required. You can also write the create table part in lowercase. And the table name is usually the same. It has the same requirement as you see in a common programming language as an identifier. So basically, that would include letters, like uppercase letters, lowercase letters, like digits, underscore, and some systems may have some variants about what is allowed as a table name. Some may just conform to the standard. Well, in reality, I guess in most cases, you just want to use the name. You just want to use the letters, digits, and underscore, right? And for column name, basically, it has the same requirement. And for data types, these are just some example of the standard types. As you can see, basically, it covers everything, a lot of things you can see in a common programming language. So first, you have character. There are actually multiple ways to write that. You can just write this CHAR, or you can write it in a word, character. And in the bracket, you specify an n. That's to say this is an n length character string. So that means if your column has the type of character n, everything in this column will have exactly the same length of n. So that's the meaning of the fixed length. What the fixed length means here. So one thing to note, suppose you have a column, say its name, and its type is character 10. Suppose that is the same, right? So you might have multiple names here. If I just write 10 letters, A, B, C, D, E, F, G, H, I, J, right? That's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Then this string will, this is just a string of 10 characters, right? That's fine. But what if, as a user, you input just A, B, C, D, E? So if you do a select name, suppose this table is called T. From T, what will you get as the result?
You get both back, but there will be spaces on the end of the second one.
Yes, there will be some filling, not exactly, there will be some filling character at the end of this. Typically, it's not space, it's actually the null character, which has the the value 0 there. Just like something like in C, you have 0 value at the end of the string. Here, you have, so for the first one, it's basically just literally A, B, C, D, E, F, G, H, I, J. That's all the characters for the first answer. For the second answer, it will be A, B, C, D, E, and 0, 0, 0, 0. It will be something like that, right? So this won't make a difference if this is shown on your command prompt or SSH. Like if you use MySQL or pSQL, this will be shown as the space. It's the, if you look at it, you won't be able to distinguish this from a space. But if you do this in a programming way, like if you connect to the database using a JDBC, a Java database connector, then what you do is basically you have you can call something called get. I don't know exactly the interface, but it's something like get string, right? And this is the first field. The first one is easy. Basically, you get back a string of 10 characters. That's fine. But for the second one, it's a bit different. Basically, you have a string of less 10, but the last 5 characters of this string will be null. So that's something you might want to be careful about, because in Java, you don't usually need to worry about the null characters here. But I think in JDBC, I'm not exactly sure how they handle this, but I would say be careful about this null at the end, right? Because that is not something you usually deal with in that language. Better alternative is to declare this as a variable length character string. That's to say var char 10. So basically, this means the maximum length is still 10, but if you have less than 10 characters in the string, then it will just return whatever is in the string. So if I still do this select name from T, what you get back is just exactly this string. So for the first one, it's still the 10 characters. For the second one, it will be A, B, C, D, E. That's the var character. Yeah. And so, any questions about this? No? Okay. Yeah.
Why would you want to return the string without the values?
Oh, that was because, so this character 10, it's a fixed length. So that actually declares you want all your strings have exactly the same length, right? But this is just a little bit weird. This is related to your user interface. So some people will not provide a full length string, like if you specify this as a length 10 string, but in your command line, you just enter 5 characters. So what does the database system do? Basically, it will follow what you said about the type. It will make sure in the end, in the system and as the output, it will give you like 10 characters. Yeah, why would you ever use that? Yeah, I would say if your string is variable length, don't use character 10. I don't find a good reason to use that. If that's the case, you should use the varchar instead. Yeah.
So is like using a card rather than like for some memory addition.
Yes, exactly. So for a car, as you can think about, I think in normal, ordinary, or like all database systems, for car, because you already know the length, you do not need to store this with each tuple, right? But with varchar, you might want to make some optimizations. Suppose your maximum length is 10, but why not just use whatever your string takes? Like, if you only have 5 characters there, why do you want to actually occupy 5 bytes there? No, 10 bytes instead of 5, right? But then you must have to have some way to mark how long this string is. So that includes some problems because this is variable length. Because when you store this, you must somehow store this information inside your tuple. Alright. So that's why we have these distinctions. But of course, this is not reflected in the SQL standard. The SQL doesn't say anything about the efficiency of this. It's basically just, in reality, in system implementation, this all depends on your system. Whether it's a SQL Server or MySQL or Postgres. They might have dramatically different choices and will have different performance across these data types. Just as a rule of thumb, I would say if your character string is variable length, just use varchar, varcharacter. If your character string is just say an ID or a social security number, that's fixed length, right? Just use a character. That eases your life and improves the performance. Alright. And the next thing is small int, integer, and big int. That's basically what we say short int and long or long in C or C++. That's just sign 2 for 8 bytes integers. And the next one is called numeric. Numeric is something like high precision number. It's something like you want a very large number in a very exact way. Say you have a banking application. You have a lot of accounts, and you want to have their balances exact. So their precision is exactly 2 digits after the after the dot, right? So how do you do that? Basically, you can use a numeric. Sometimes it's also called a decimal. So the P is the number of digits you want, including those after your decimal. S is the number of I think S is the number of digits after that dot. So, and you also have floating point number. Real is basically single points. That's float in C, and double, that's just as its name. So it's double floating point numbers. And you have date, time, timestamp. Date is just say today, like August 30th, 2018, right? Time is the clock, is the time, like this is now is 1:31 p.m. That's the time, and timestamp is two things combined. Let's just say 1:31 p.m. on today, August 30th, 2018. Right, that's the timestamp. And serial is a special type that is for generating unique IDs for indexing and cross-reference. You can think of that as like unique IDs like 1, 2, 3, 4, 5. That's something convenient to use, right? So the next thing to talk about is called the column constraint. So in SQL, you can specify the column constraints in 2 parts. Sometimes you can specify at the end of your column list, like you can first define what your column names and data types are, then define this column constraint. Yeah, or as is shown here, you can also do just append that to a column definition. So here you can use constraint name. This is optional. And what you can specify is basically not now or now. Not now basically means you cannot specify a null value there. Null value is something that's not applicable. You can also specify unique. Unique tells database this is a key. Or more exactly, this is a super key. Alright? So since it's a single column super key, so it's of course a candidate key. But when you use unique instead of primary key, that's when you have multiple keys, but only one of them can be primary key, right? The remaining candidate keys, if you want the database to enforce that for you, then you can specify the unique here. Basically, unique tells that it's not a primary key, but it's also a key of my database. Then this check brackets expression. In the expression, it can be a general expression. So basically, involving this column. So suppose you want to say this column should be all greater than 5. Then you can write this column is greater than 5 in the check here. And also this references is foreign key constraints. It basically says this is a foreign key that references another table, and the column is called this. If the column has the same name, probably you won't need to have to specify the name in another table. But if they are not the same, then you have to. And here, this two, on delete and on update action is basically what we talked about. When you delete some prime key in one table, well, you still have a foreign key in another table that references this primary key. What do? You can have multiple actions, so you can basically do nothing. That means you do not allow deletion of that primary key, because otherwise you have a dangling pointer, right? Or you can do this cascading abort. No, sorry, not abort. Cascading deletion or updating. That's to say, so suppose you delete a primary key 1, and there's a foreign key 1 referencing this key. So if you delete that primary key 1, it also deletes all the records with this 1 as a foreign key. That's what cascade says. Or you can also use this set now or set default. So set now basically sets the value to a default value of now. Of course, you cannot specify not now in your column. Otherwise, it doesn't make sense, right? If it can be now, that means you use a now here, then this set now will work. Like you will set this foreign key to now. Or you can use set default. Basically, you set that to a default value you specify, right? So, yeah. Any questions about this so far? No? Okay. And as the final part is called table constraint. So table constraints may contain more things, like you can still specify primary key and unique keys here, but what's the difference from this and if you specify that in column constraints? The only difference is that here you can also do single column primary key, but here you can also do multiple column primary keys. So suppose your key is a combination of SID and SNAME, then you can specify that in the primary key, SID, comma, SNAME. Then the system will know your primary key is a 2-column key, right? And also that also applies to unique. Basically, you can specify a multi-column non-primary candidate key. And also you can also do check here. This check is more general than the check in column constraints because you can reference all the columns in your table here. And foreign key, this is the same. Basically, if you specify for references directly in the column constraint, you cannot use multiple columns. But here you can use multiple columns. Suppose you are doing, say, one table has a 2-column primary key. Your 2 columns in this table want to reference those 2 columns. Then you must do it here in table constraints. You do foreign key, those 2 columns, references another table, and those 2 columns. And the same thing applies. You can also do on delete and on update. That's the same as before. So, yeah. Does that make sense to us, everybody? Yep.
I had a question on the on delete and on update.
Yep.
Does that apply to a specific column when you put it as a table constraint, or does it apply to the table?
Yes, so this will apply to the foreign key columns.
Okay.
All right. So here's a possible example. Suppose you want to create a table of films. and you have its code as a primary key, fixed length character string. If you know, it's just 5 characters. And you have its title. Of course, movies have different lengths of titles, right? And you have this PID. I don't know what this PID is. And you have the date of production as date, and you have kind. Say it's comedy or romantic, right? And you have different constraints, like you say the date of production is also a key, right? And also you have this foreign key constraint, DID references. Oh, distributor, so that's distributor ID, right? Don't distribute this field. And also you have a second table called distributor, and DID is its primary key. It's referenced by the film table. And it has more constraints. This is a general constraint, I said, as a table constraint. And it has a name of cons1. And the thing it checks is that the DID should be greater than 100. And the name should not be empty. Something what this says. So if you try to insert something with a DID smaller than or equal to 100, or with an empty name, then the database system won't let you. Basically, it will reject the insertion. Or if you update something to that, it will also reject this update. So be careful about this a little bit, because when you do this in a real database system, make sure the database system will tell you, I don't know what that distributor is, so I cannot do that. Right? So if you have cyclic references, which is a sign of bad design, I would never encourage. But if you do, I think the only way to do that is use alter table. That's to say, once you create a table but without a bunch of constraints, then you alter those constraints later. Use an alter table statement. So yeah, that's about it. The last part? Yeah. So suppose you have a cyclic reference, like films table references this DID and then this name references something else, then it forms a cycle. Then you cannot do that directly. Alright, so yeah, that's about the DDL. We just showed the create table thing. We didn't show like job table, order table, because you can, if you want, you can just look up your specific database. They have documents for that. We just covered the most important thing here. So the next thing to talk about is called the single DML, data manipulation language. So I think this is a little bit outdated. Like when I search online, there's actually somebody put this select statement into a third category called query language. Anyway, this is just a name issue. So basically, data here, what we mean by data manipulation language is that you can manipulate the data. You are not dealing with the schemas. You are dealing with the data themselves. So you can query the data, you can update the data, you can insert, you can delete, right? So they are all in this category. So suppose we have this students table here, and you want to find all the 18-year-old students, you can just write this statement. So for those who have never touched Seagull before, does this make sense to you? Can you understand this without any explanation? Who finds this intuitive? Please raise your hand. Yeah, so yeah, that's a little bit surprise because this is supposed to be more like a natural language. Of course, not syntactically that way, but it's supposed to convey a meaning that is intuitive to even a regular user. So anyway, this is just to say we want to select everything and from the student table, and we want to only select those with an edge of 80. That's what this statement says to satisfy our query. And if you just want to find the names and logins, you can just do a projection here. Projection corresponds to the select part in your SQL statement. You can just list s.name and s.login there, right? So if you want to query multiple tables, that's actually join. Typically, it's a join or cross product. So here, as you can see in where, you need to specify s.sid equal to e.sid. So anybody can tell me what this corresponds to in relational algebra? Yep.
Isn't this a cross product?
Yeah.
And then you do a selection on that cross product where the two IDs are equal and the grade is going to be.
Yes, that's correct. That's one way to say that. Or can you express that in another way?
So the optimizer will change it to be a natural join on the SID with a selection of e.grade.
Yes, that's correct. So yes, so typically a database will optimize this into a join, and it will first do the selection on row table on grade to be B, then use that as a natural join base table and a student table, right? So use that to do a natural join, and this way you will get the student's name and course ID. Who the students did a B grade in that course, right? So that's querying multiple relations. So I think time's almost up, so maybe I'll stop here. And next time we will continue to go through all the SQL part. And also because next week we will be releasing the labs. So if you want to take a overview of the labs, please make sure you contact